Welcome to part 1 of our explainer on satellite positioning basics. Today, we're diving into how you actually know where you are out on the water, looking at GPS, DGPS, and GNSS. Have you ever wondered how these massive ships, carrying literally millions of dollars of cargo, know their exact spot on a seemingly endless ocean? Well, let's set the scene.
Picture this. You're 200 miles from the nearest coastline. It's 3 a.m. There is no lighthouse, no landmarks, nothing but pitch black water in every single direction. It's kind of terrifying if you really think about it. In this environment, trusting your instruments isn't just, a best practice. It is an absolute matter of survival. You can't just guess. You have to know exactly where you are.
Now, just 60 years ago, ship officers navigated this exact same blackwater situation using a sextant, a highly accurate clock called a chronometer, and, honestly, a massive amount of manual math. It was slow, it was completely weather-dependent, and through a process called dead reckoning, the margin of error just kept accumulating the longer you were at sea. But today, you just glance at a digital screen and boom, you get your position with sub-meter accuracy. That massive leap didn't just happen by accident. So, how does this seemingly magical black box technology actually work? Let's pull back the curtain.
Section 1. The Basics of GNSS.
When we talk about this tech, almost everyone just defaults to saying GPS, but GPS is technically just the United States-specific system. The overarching, much more accurate term we should be using is GNSS. That stands for Global Navigation Satellite System. It's a broader term, and it encompasses multiple satellite networks, including Russia's GLONASS and Europe's Galileo. It's this combined mesh of satellites orbiting the Earth that actually allows receivers to lock down those precise global coordinates.
So in practice, up on a ship's bridge, GNSS is continuously feeding data straight to the navigation screens. We aren't just talking about a static dot on a paper map anymore. Because old-school celestial navigation is slow and errors build up over time, satellites solve that problem by handing you a fresh, incredibly precise fix every single second. It gives you continuous latitude and longitude, for sure, but also critical movement metrics like your speed over ground, or SOG, and course over ground, your COG. We see the final result right there in front of us, but how is that receiver actually pulling that precise data from hundreds of miles up in space? Let's get into the physical mechanics.
Section 2. Calculating your exact position.
Here's the crucial thing to understand. Your receiver is constantly running a highly elegant math equation over and over again. It works in 3 steps. First, a satellite broadcasts its exact position in orbit along with a super precise timestamp of exactly when that signal was sent out. Second, your ship's receiver listens for that radio signal and times exactly how long it took to arrive. And third, because radio waves travel at a known constant, the speed of light, the receiver just multiplies the speed of light by that travel time to figure out the exact distance to that specific satellite.
Conceptually, this is just fascinating. Every satellite is basically drawing a giant sphere of possible distance around itself. If you only talk to one satellite, well, you're somewhere on the surface of that massive sphere. Add a second satellite, and where those 2 spheres intersect forms a circle of possibilities. Add a third satellite, and those 3 spheres will eventually intersect at just a single point on the Earth's surface. That single intersecting point, that is your ship. Now, that brings us to the absolutely most crucial and often the most misunderstood technical reality of satellite positioning.
Section 3. The 4-Satellite Rule.
I want to pause for a second here and challenge your spatial assumptions. We just established that 3 intersecting spheres narrow down your 3D position, right? Latitude, longitude, and altitude. So, why does a GNSS receiver absolutely mandate a minimum of 4 satellites in view to give you a valid fix? If 3 gives you a point on the globe, what on earth is the 4th one actually doing?
Well, the answer is a pretty dramatic twist, and it comes down to this number, 300 meters. See, the atomic clocks on board the satellites are incredibly, practically perfectly precise, but the internal quartz clock inside your ship's receiver, it's relatively cheap, and it drifts. Because we are multiplying by the speed of light, just 1 single microsecond of drift in your receiver's clock translates to roughly 300 meters of position error. Literally 3 football fields of error from a 1 microsecond glitch. No way you can navigate with that.
So the solution to that terrifying problem is downright ingenious. Satellites 1, 2, and 3 are indeed solving for your 3D position. But that 4th satellite, it's not for position at all. It acts as a vital corrector for your timing drift. By communicating with a 4th satellite, the receiver can treat its own clock error as a 4th unknown variable in the algebra.
It's essentially recalibrating its cheap internal clock against the perfect atomic clocks floating out in space. Without it, your data is dangerously useless. All right, we've got the foundational math down, but we are far from done. Let's look at the limitations of the raw data we just learned about.
Section 4. Up next, refining accuracy.
So let's summarize the key takeaways from Part 1 of this explainer. GNSS calculates your position using the timing of radio signals. You absolutely must have a minimum of 4 satellites to get a fix, because that 4th satellite is strictly there to cancel out your clock error. But here is the major catch. Even with a perfect 4-satellite lock under completely open sky, raw, standard GPS accuracy still has an error margin of about 5 to 10 meters. Now, out in the open ocean, 10 meters is nothing. But if you're navigating a massive container ship into a narrow harbor channel with only meters of clearance on either side, that raw error margin is more than enough to cause a multi-million-dollar grounding.
Which leaves us with a pretty massive operational problem. How do we fix that 10-meter margin of error? Well, in Part 2 of this explainer, we're going to look at how shore-based stations use a system called DGPS to dial that fix down to sub-meter accuracy. We'll also dive into the terrifying reality of signal spoofing and the specific warning signs you need to spot to know when your bridge equipment is actively lying to you. Because if we're trusting these screens with our lives, what exactly happens when they start telling us a mathematically perfect lie? Stick around and join me in Part 2 to find out.